Example number 3 is a steel framed floor for an office building that was designed to support a live load of 50 psf and a dead load of a concrete slab with a density of 150 psf, a steel decking with a weight of 5 psf, mechanical equipment 10 psf, suspended ceiling 5 psf, and then for beams and girders. So beams and girders, we also have the dead load, 25 PLF and 35 PLF. The question is asking, using appropriate FBDs, determine the reaction forces for beams B1, B2, and B3, and then also girder G1. So we're looking first at beam B1, then we will look at free body diagrams of beam B2, then beam B3, and then finally girder G1. So this is B1, B2, B3, and girder G1 is here. So we need to look at the detail of the connection of beam to girder. So here we have beam B4 connected to girder G1. In this detail, which is here in our plan, we can also see the details of the flooring system, which is consisted of a 4-inch thickness slab, and then we have a steel deck. So we need to calculate weight of flooring system that we have, which is consisted of a concrete slab with a density of 150 pound per cubic foot, a steel decking, mechanical equipment, and suspended ceiling. They're all in PSF. So we can add them together, but pay attention that for concrete we have density. So we need to calculate weight per unit area. And in order to do that, you just need to multiply density of concrete by thickness. And since the density is pound per cubic feet, we have feet here, we need to convert 4 inches to feet. So we need to divide this by 12. That's the conversion of inch to feet. So 4 inches, that's the slab thickness. Here. 12 here is to convert inch to foot. And here we have density of concrete, which is 150 pound per cubic feet, which is given to us. So now we have the slab load in pound per square foot, or PSF. And the rest of the detail of the flooring was already provided in pound per square foot, pound per unit area. So we can add all of them together. Dead load of concrete slab is 50 psf plus 5 plus 10 plus 5. The total dead load is 70 psf. We also have the total live load. So dead load plus live load. 70 plus 50. The area load that we have here, the area load or the total dead load and live load is 120 PSF or pound per square foot. So we have the area load and it's supported. If we look at the load path, it's from the area to the beam. So we have from the flooring system to the beam to the girder. The area is supported by 1, 2, 3, and 4 beams. First, we want to look at free body diagram of beam B1 and calculate the load transferred from the area to beam B1. If you remember, in order to do that, we said that we need to find tributary width. Tributary width for beam B1 is half of the distance between beam 1 and its adjacent members. Beam B1, it only has one adjacent member. Beam 2, the distance between beam B1 and B2 is 12 feet. So half of that distance is 6 feet. And that's our tributary width. That is the tributary width for beam B1. Again, right now we are looking at beam B1 here. And half of the distance between beam 1 and beam B2 is 6 feet. So that's tributary width of load for beam B1. And we said that area load is 120. And again, if you remember, we said that the load on a beam supporting an area is equal to area load that we have, and this area load is the total dead load and live load, times tributary width. So the area load that we have here is 120 pounds per square foot, and tributary width of load for beam B1 is 6 feet. So this is our area load, dead load, and live load. Total area load that we have, 120 PSF times tributary width. And then we also need to add dead load of beam, which was given to us. So dead load of steel beam is 25 PLF. So if you add everything together, the load on beam B1 is equal to 745 PLF. Now we want to calculate the end reactions. So we have a uniformly distributed load, 745 pounds per foot, and the length here, this total length here is 20 feet. So we have 20 feet here It's a simply supported beam, symmetric, so the reactions are equal to 745 pound per foot times length, which is 20 feet, divided by 2. Again, load times length divided by 2. So these are the reactions that we just calculated. These two end reactions of beam B1, each one 7,450 pounds. Same thing here. And these two loads are transferred to the column. Again, pay attention to the detail. Beam B1 is connected to the web of the column section, which means that the load is transferred to the column, not to the girder G1 or G2. The load path here is from beam to column. Okay, so this was for beam B1. Now we want to look at beam B2. Here, this is beam B2, and it has two adjacent members, beam B1 and B2. So tributary width is half of distance on the left side and half of the distance on the right side. 6 feet plus 6 feet. So tributary width of load for beam B2 is 12 feet. Now we want to calculate how much load is transferred from the area to beam B2. We need to multiply dead load and live load that we have, which is 120, by tributary width. So again, this is our dead load and live load times tributary width, and then we need to add dead load of beam. So the magnitude of the linear load applied to beam B2 is 1465 pound per foot. Now we need to calculate the end reactions here and here for these two end reactions. And again, we have simply supported beam end reactions are equal to each other because it's symmetric. So end reactions are equal to load times length divided by 2. So 1465 pound per foot times 20 feet divided by 2. Now pay attention to the details of the plan. These two loads are transferred to the girder. So at these endpoints where beam is connected to the girder, 14,000 pound is transferred from the beam to the girder. We're done with beam B1 and beam B2. Now we want to look at beam B3. But what you need to pay attention is that there is an opening here. So where there is an opening, it means that there is no load in this area. So for the top, for this section of beam B3, we have two adjacent members. There's load is coming or transferred from the area on the right side and on the left side to beam B3. So for the purple section, the 12 feet section, tributary width is 6 feet on the left side plus 6 feet on the right side. So here tributary width is 12 feet. But for the rest of the beam here, where we have opening on one side, there is only one adjacent member and there is only area load on one side. So tributary width is 6 feet. So again, this is the blue section. There is only load coming from this area and tributary width is 6 feet. But for the 12 feet section, so this is 12 feet, load is coming from both sides. So tributary width is 12 feet. So if we want to draw the free body diagram, um, this is the section where we have opening on one side and then we have the section where the load was transferred from both sides. So for the section, 12 feet section here, with a tributary width of 12, we have dead load and live load times tributary width, and then we added dead load of beam. So here for this section, the load is 1465 PLS. And then for the 6 feet span, we have dead load and live load times tributary width, and then we added dead load of beam. So this is dead load of beam, and that's how much load we have here, which is 745 pounds per foot. So this is free body diagram of beam B3, but this is not symmetric. So because it's not symmetric, we can't say that R is not equal to load times length divided by 2. because it's not symmetric, again, one more time, we can't say the reactions are equal to each other and they're equal to load times length divided by 2. Instead, we need to use equations of equilibrium. So we have point A and B. We're going to call this BY and this one AY. These are not equal to each other. And we're going to write, so we're going to use equations of equilibrium. And we're going to write sigma m sum of moments around point A is equal to 0. And I'm going to replace the linear loads that we have with the resultant. So if you remember, we said that the resultant for a rectangular load is equal to load's magnitude times length. So resultant of W3 is equal to 1465 PLF times 12 feet. And resultant of W4 is equal to 745 times 8 feet. And this is 4 feet away from point A. And this one is 8 feet plus half of 12, which is 6, which gives us 14 feet. So here, 4 feet away, I have the resultant of W4, which is 745 times 8. And here, 14 feet away from point A, we have 1465 times 12. So now let's look at the formula for sum of moments around point A. A1 passes through point A. So the distance is 0 and the moment is 0. Then we have this one, which is the resultant of W4, and the distance is 4 feet. And around point A, it will cause a clockwise moment. So the moment of this load is clockwise, and we're going to use a negative sign. Then we have the resultant of W3. So this is the resultant of W3. And the distance from point A is 14 feet. This one also around point A will have a clockwise moment. And then finally we have BY, which is 20 feet. From AY or point A, and it will cause a counterclockwise moment, which we will use a positive sign for. So if we want to write down sum of moments around point A, we have resultant of W3 times distance. This is distance of resultant of W3 from point A. And we use a negative sign because it's clockwise. Then we have the second moment, which is resultant of W4 times distance. And again, we are using a negative sign because it's clockwise. And then finally, we have reaction at point B times distance. And we are using a positive sign because we have a counterclockwise moment. And when you solve this, you get reaction at point B is equal to 13,498 pounds. Now we want to solve for AY. We have the resultant here, downward, so we're going to use a negative sign. This is the resultant of W4. This is the resultant of W3, which is again a negative sign for downward load. We just calculated reaction at point B, it's upward, so we're going to use a positive sign. And what is missing is AY. So we're going to write the formula for sum of forces in the Y direction are equal to 0. We have resultant of W4, negative for downward, minus resultant of W3, plus BY plus AY is equal to 0. And now you can find AY, reaction at point A. So we calculated the end reactions here, here, and here. But as I said earlier, we don't need this one because the reaction of beam B1 is transferred to this column. It doesn't go to the girder. So when we are looking at the girder, the two reactions that are important for us are from beam B2 and beam B3. Because it's the same thing with beam B4. B1 and B4 are connected to the web of the column. The load from B1 and B4 is transferred to the column. B2 and B3 are connected to the girder. So this is the detail of B2 and B3 connection. And as you can see, they're connected to the girder. So the end reaction of these two are the loads transferred to the girder. And we have the numbers from the previous slide. So if we want to draw free body diagram of girder G1, where beam B2 and B3 are connected to the girder, we'll have 2-point loads. B2 from previous slide, we have 14,650 pound, and beam B3 on this side transfers 13,498 pounds. And we need to calculate the end reactions. But other than the 2-point loads that we have, we need to also consider dead load of girder, which was provided to us in the first slide of this question as 35 pounds per foot. So we have this linear load, which is dead load of girder, and is equal to 35 PLF. So again, in this example, because the magnitude of these point loads are different, then it's not symmetric. So RB is not equal to RA. RA is not equal to RB, and we cannot use R is equal to load times length divided by 2. We actually need to use equations of equilibrium. So we have point A, that's point A. We have load B from B to beam B2, that's the load, 14,000, times distance, which is 12 feet. It has a clockwise moment around point A, so we'll use a negative sign. 14,000 times 12 feet with a negative sign. Then we have load from beam B3. Distance is 24 feet, and the clockwise moment around point A, so a negative sign. Load times distance from point A and a negative sign because it's clockwise. Then we have the dead load, and we're going to replace it with the resultant. So this is the resultant of W girder, dead load of girder. It will be equal to 35 PLF times total length, which is 36. So here we have 35 PLF times 36. And distance of this loop from point A is 12 plus 6, which gives us 18 feet. This one also causes a clockwise moment around point A, and we're going to use a negative sign. So 35 times 36 is the resultant. Distance is 18 feet. And then finally we have BY, and it's 36 feet away from point A, and the moment is counterclockwise, so we're going to use a positive sign. And you can calculate reaction at point B or BY. So we have reaction at point B or BY. Now we need to calculate AY. We have 14,000 downward, so we're going to use a negative sign. We have another 13,000 downward, so we go again. We're going to use a negative sign. We have by upward, so positive sign, and we have the resultant of the girder's weight. So we have resultant of weight of girder, which is 35 PLF times total length, which is 36. It's downward, so we're going to also use a negative sign here. And then we have upward reaction at point A, and then we can solve for reaction at point